China is building a permanent base on the moon, while the United States is still trying to figure out how to get there consistently. That sounds exaggerated until you look at the timelines. China is laying out a step-by-step roadmap to construct a functioning lunar base by the early 2030s. Not a visit, not a mission. A base designed to operate continuously at the moon's south pole. Meanwhile, the Artemis program is still dealing with delays, redesigns, and systems that haven't all worked together yet. And here's the part most people miss. This isn't about who lands first anymore. It's about who builds first. Because once a base exists, power systems, habitats, resource extraction, everything changes. You're not competing with a landing. You're competing with an operating system already in place. So the real question isn't whether the United States can reach the moon. It's whether it's already too late to catch up. Because to understand that, you have to see how differently these two systems are being built. Not about landing. You're watching a race that most people still misunderstand. It looks like a repeat of the past rockets launching, astronauts preparing, headlines building toward the next moon landing. And naturally, your mind goes to one question: who gets there first? But that question is already outdated. Because this time, landing isn't the goal. It's the minimum requirement. Back in the earlier era of space exploration, reaching the moon was the finish line. Astronauts landed, planted a flag, collected samples, and returned home. The mission was complete the moment they left the surface. There was no intention to stay, no infrastructure left behind, no system designed to continue operating. And once that moment was achieved, everything slowed down. But what you're seeing now operates under a completely different objective. Today, the moon is no longer a destination. It's a location where something permanent is being built. And that changes the entire definition of winning. Because a single landing doesn't create control. A system does. That system includes power sources that can run continuously, habitats that can support human life for extended periods, communication networks that stay active, and logistics systems that allow repeated missions without starting from zero every time. And this is where the gap begins to open. Because one side is still talking about returning to the moon. The other is preparing to live there. But this was just the beginning of the shift. The moment you move from short missions to permanent presence, everything becomes more difficult. You're no longer solving for survival over a few days. You're solving for sustainability over months, even years. You need reliable energy, protection from radiation, systems that don't fail under extreme conditions. And the moon doesn't make that easy. Temperatures swing from hundreds of degrees in sunlight to extreme cold in shadow. There's no atmosphere to shield against radiation. The surface itself is abrasive, unpredictable, and difficult to build on. So building a base isn't just a bigger version of landing. It's a completely different problem. And it wasn't just the engineering that changed. The mindset changed with it. Because now, every mission has to connect to the next. Every system has to support something beyond itself. You're not launching isolated missions anymore. You're assembling a structure piece by piece in one of the harshest environments imaginable. And that requires clarity. You need to know what you're building before you start. Then came the realization that defines this entire race. You don't win by showing up. You win by staying. Because the moment a nation establishes continuous operations on the moon, the dynamic changes instantly. They're no longer visiting. They're operating, expanding, improving systems while others are still planning their next step. And once that happens, catching up becomes harder than it looks, because you're no longer competing with a mission. You're competing with a system that's already running. Then the question shifts again. Not who will land first, but who is already building something that won't leave. China builds systematically. You're looking at a program that doesn't rely on big moments to prove progress. There's no single launch that defines everything. No dramatic turning point that decides success or failure. Instead, what you see is something far more controlled and far more difficult to stop. A system that keeps moving forward, step by step. At first, it feels slow, almost quiet, but that's exactly how it gains momentum. China's approach to the moon follows a clear sequence that doesn't break. Robotic missions come first, orbiters mapping the surface, landers testing precision, rovers exploring terrain. Each mission focuses on one capability at a time, solving specific problems before moving forward. Landing accuracy, surface navigation, remote operations. Then comes one of the most critical milestones: bringing material back from the moon. China successfully completed a robotic sample return mission, collecting lunar material and delivering it safely to Earth. That achievement places it among a very small group of nations capable of completing the full cycle of a lunar mission launch, land, operate, and return. And that moment changes everything. Because once you can complete that cycle, you're no longer experimenting, you're repeating. But this was just the beginning of the pattern. Each mission feeds directly into the next. There are no resets, no sudden changes in direction. The objective stays consistent from the start: build toward a permanent presence on the moon, and every step reduces uncertainty before the next phase begins. That creates a different kind of progress. Not explosive, but reliable. Then comes the shift that most people overlook: cargo. Before humans arrive, China plans to send equipment ahead of time. Autonomous systems that can prepare landing zones, begin construction, and test infrastructure before astronauts ever step onto the surface. And that changes the entire timeline, because instead of sending humans into an unprepared environment, they arrive at a site that's already partially operational. Then came the bigger move: the International Lunar Research Station. Not a temporary base, not a short mission. A long-term system designed to operate continuously at the moon's south pole. Power systems, habitats, communication networks, all planned as part of a single structure that expands over time. And it wasn't just about building alone. China begins forming partnerships, inviting other nations to participate in the system, sharing access, offering collaboration, creating a network that grows around the base rather than competing against it. That's where the strategy becomes clear. This isn't about racing to a moment. It's about reaching that moment with everything already aligned. Because when you move this way, every success compounds, every mission lowers risk, every system connects to the next, and over time, progress stops looking like individual achievements and starts looking like a machine that builds itself. And it wasn't just the speed that matters, it's the direction. Because when every step points toward the same outcome, you don't waste time figuring out what comes next. You already know. Then came the realization that shifts how you see this entire program. China isn't trying to prove it can reach the moon. It's proving it can operate there. And if that system reaches the surface before anyone else has fully aligned their own, then the advantage doesn't start at the landing. It starts long before it. But across the world, a very different kind of system is trying to come together. Centralized power advantage. You're looking at two completely different machines trying to reach the same destination. On the surface, both aim to return humans to the moon. But the way they move, the way they make decisions, the way they solve problems, couldn't be more different. And that difference starts at the top. China operates through a centralized system. One direction, one chain of command, one long-term objective that doesn't shift with every new phase. When a decision is made, it moves straight into execution. There are fewer competing priorities, fewer delays caused by coordination, and far less friction between the parts of the system. And that creates something powerful: continuity. Projects don't reset. Timelines don't constantly change direction. The same vision carries through every mission, from early robotic exploration all the way to building a permanent base. That consistency allows each step to connect tightly to the next. But this was just the beginning of the advantage, because centralization doesn't just affect speed, it affects integration. When one system controls development, hardware, and mission planning, everything is designed to work together from the start. Landing systems align with cargo systems. Power systems align with habitat designs. Communication networks are built with future expansion already in mind. Nothing exists in isolation, and that reduces risk. Because instead of solving compatibility problems later, they're solved before they even appear. Systems are built as parts of a whole, not as separate pieces trying to fit together under pressure. Then came the contrast that starts to create tension. The United States operates very differently. Its system is distributed across multiple agencies, private companies, contractors, and international partners. On one hand, this creates innovation. Different groups bring new ideas, new technologies, and new approaches. But on the other hand, it introduces complexity that slows everything down because every piece has its own timeline, its own priorities, its own constraints, and aligning all of that takes time. But the silence didn't last, because when one system depends on another, delays don't stay contained. If one component falls behind, others have to wait. If a design changes, multiple systems have to adjust. And over time, those dependencies start to stack. Then came the most difficult part. Coordination becomes the bottleneck. Instead of focusing purely on execution, time is spent aligning decisions, negotiating responsibilities, and ensuring that every part moves together. And in a project as complex as returning to the moon, even small misalignments can create large delays. And it wasn't just about timing, it was about clarity. Because when multiple groups are involved, the end goal can start to blur. Different teams optimize for different outcomes. Some focus on innovation, others focus on safety, others focus on cost. And while all of these matter, they don't always point in the same direction. China doesn't face that problem in the same way. Its system moves with a single objective in mind: build the base. Everything else supports that. And that creates a kind of momentum that's hard to interrupt. Because when decisions are faster, systems are aligned, and goals remain fixed, progress becomes predictable. Then came the realization that changes how you see the entire race. Speed isn't just about technology, it's about structure. Because the system that moves with fewer constraints doesn't just advance faster, it reaches operational capability sooner. And in a race where the goal is to build something that stays, that difference may decide everything. But when that centralized system meets a program built on ambition and complexity, the gap becomes even harder to ignore. Artemis without alignment. You're looking at a program that promises everything. A return to the moon, a sustainable presence, a system that goes beyond anything built before. On paper, it feels unstoppable. But the moment you look closer, the cracks begin to show. Because Artemis isn't one program. It's a collection of systems that all have to work perfectly together. The Space Launch System is designed to carry massive payloads beyond Earth. Orion is built to transport astronauts safely through deep space. The Lunar Gateway is planned as a station orbiting the moon. And the Human Landing System, built with private partners, will take astronauts down to the surface. Each piece is powerful on its own, but none of them work alone. And that's where the tension begins. Because every part depends on another. If the rocket isn't ready, nothing launches. If the spacecraft isn't fully validated, crews can't fly. If the landing system isn't operational, astronauts can't reach the surface. If the gateway isn't assembled, mission architecture changes entirely. And the more dependencies you add, the more fragile the timeline becomes. But this was just the beginning of the pressure. The Space Launch System has faced repeated delays and rising costs, with each launch carrying a price tag in the billions. Orion has completed key tests, but still requires further refinement for long-duration missions. The Lunar Gateway introduces additional complexity, requiring multiple launches and international coordination before it becomes functional. And then comes the landing system, a critical component that still depends on technologies being tested, refined, and scaled at the same time. That's where the gap starts to widen. Because while one system is still assembling its parts, the other is already moving through its sequence. Then came the most difficult realization. Artemis is trying to do everything at once. Return humans, build infrastructure, create partnerships, develop new technologies, all within a single framework that has to come together under pressure. And while that ambition is powerful, it slows execution. Because every layer adds another point of failure. Every innovation adds uncertainty. Every dependency adds delay. And it wasn't just engineering that made it harder. It was alignment. Different contractors working on different timelines. Different agencies managing different components. International partners contributing pieces that must integrate seamlessly. And each of these moving parts has to stay synchronized for a mission to succeed. But the silence didn't last, because delays don't stay hidden. They push timelines forward. They force redesigns. They create gaps between what's planned and what's actually ready. And over time, those gaps begin to define the program. Then came the shift that changes everything. The goal of Artemis is still evolving. Is it about landing astronauts, building a sustained presence, creating a long-term system? The answer includes all of these, but that lack of a single, fixed endpoint creates friction, because when the target moves, execution slows. And that's where the contrast becomes impossible to ignore. One system is building toward a clearly defined base. The other is still aligning how all of its parts come together. And in a race where timing matters more than perfection, that difference starts to compound. Because while Artemis works to bring its system into alignment, time keeps moving. And the moment another nation establishes a functioning base first, the entire dynamic changes. Because you're no longer competing with a plan, you're competing with something that already exists. Then the question stops being how advanced Artemis is, and becomes whether it can come together before that moment arrives. Building on the moon. You might think the hardest part of this race is getting there. Launching rockets, navigating deep space, landing safely on the lunar surface. And for decades, that was the challenge that defined everything. But this time, reaching the moon is only the beginning. Because building on the moon is an entirely different problem. The moment you try to stay, the environment starts pushing back. Temperatures on the lunar surface can swing from over 250 degrees Fahrenheit in sunlight to nearly -300 degrees in shadow. You heard that right. A difference so extreme that most materials expand, contract, and break under repeated exposure. And unlike Earth, there's no atmosphere to soften that change. Then comes radiation. Without a protective atmosphere or magnetic field, the moon is constantly exposed to cosmic radiation and solar particles. Over time, that exposure becomes dangerous for both humans and equipment. Electronics degrade, materials weaken, and astronauts face long-term health risks if they remain unprotected. But this was just the beginning of the challenge. The surface itself creates problems. Lunar soil regolith is not like the soil on Earth. It's sharp, abrasive, and sticks to everything. It can damage equipment, interfere with moving parts, and create hazards for long-term operations. Even simple tasks like sealing habitats or maintaining machinery become more complex in this environment. And then there's gravity. The moon's gravity is about 1/6 of Earth's, which affects everything from how structures are built to how the human body functions over time. Muscles weaken. Bone density decreases. Systems that work perfectly on Earth have to be redesigned to operate in low gravity. So building a base isn't just about placing structures on the surface. It's about redesigning how those structures survive. And that's where the next shift begins. Because instead of bringing everything from Earth, the focus moves toward using what's already there. Regolith becomes a building material. Advanced systems can process lunar soil and turn it into solid structures, walls, landing pads, protective layers. Some designs use three-dimensional printing to construct habitats directly on the surface, reducing the need to transport heavy materials from Earth. And that changes everything. Because the more you can build locally, the less you depend on launches from Earth. And every pound you don't have to launch saves thousands of dollars. You heard that right. But it wasn't just about construction. Autonomous systems play a critical role. Robotic units can prepare landing sites, level terrain, and begin building structures before humans even arrive. That means astronauts don't start from zero. They arrive at a site that's already partially operational, already tested, already structured for expansion. Then comes the question of power. A base cannot survive without a constant energy supply. At the moon's south pole, certain regions receive near-continuous sunlight, making solar power a primary option. But because shadows can last for extended periods, backup systems, possibly nuclear, become necessary to ensure stability. And that's where everything connects. Energy powers construction. Construction supports habitation. Habitation enables continuous operations. And continuous operations turn a temporary mission into a permanent presence. Then came the realization that defines this entire challenge. The first nation to solve these problems doesn't just survive on the moon, it stays. And once a system like that is in place, tested, functioning, expanding it creates a foundation that others have to build around, because the moon doesn't reward those who arrive. It rewards those who can remain. Which brings the race to a single critical question: where exactly that first base will be built, and why that location changes everything. South Pole Advantage. You might think the moon is one vast open landscape where anyone can land anywhere, a blank surface waiting to be explored. But the moment you look closer, that illusion starts to disappear. Because not every part of the moon is equal. In fact, only a small portion of it truly matters, and that portion sits at the South Pole. This region doesn't stand out visually. It's rough, shadowed, and difficult to navigate. Craters stretch across the surface, many of them permanently dark. But inside those shadows lies something that changes the entire value of the moon. Water. Not liquid, but frozen, in massive quantities within those craters. Protected from sunlight for billions of years, this ice has remained stable, waiting beneath the surface. And the scale is staggering. Estimates suggest hundreds of billions of pounds of water ice could exist in these regions, enough to support long-term operations for years, possibly decades. Enough to produce fuel, sustain life, and power continuous missions. But this was just the beginning of why the South Pole matters. Because right next to those shadowed craters are ridges that receive near-constant sunlight. Areas where solar panels can generate energy almost continuously, without the long nights experienced in other parts of the moon. That combination is rare. Water in the shadows, energy in the light, and together, they create one of the most valuable environments beyond Earth. But the silence didn't last, because there's a limit. These optimal zones are small. Narrow strips of terrain where access to both sunlight and ice is possible. And once those areas are occupied, the options for others become far more restricted. Then came the realization that shifts the entire race. You're not competing for the moon. You're competing for these exact locations. Because the first base built near these regions doesn't just gain access to resources, it gains positioning. It defines where landing zones are placed, where infrastructure begins, where future missions are forced to navigate around. And that advantage compounds over time. Once a base is established, it expands outward. Power systems extend range. Transportation routes connect nearby sites. Resource extraction begins feeding into operations. And slowly, that region transforms from a landing site into a controlled zone. And it wasn't just about access, it was about influence. Because any mission that arrives later has to work around what already exists. They may need to land farther away, transport resources over longer distances, build systems without the same efficiency. And that increases cost, it increases complexity, it slows them down. Then came the most important shift of all. The South Pole isn't just valuable because of what it has, it's valuable because of how limited it is. And once those key locations are taken, they don't open up again. They become the foundation for everything that follows. Which leads to the final moment in this race. What happens when one side stops visiting the moon and starts living there permanently? Living there first. You reach the moment where everything changes. And it doesn't look dramatic at first. No single headline captures it. No clear finish line signals the end of the race. Because the real shift happens quietly. One side stops leaving. At first, it looks like longer missions. Crews staying a little more time. Systems running a little more consistently. Cargo arriving more frequently. Small signs that something is stabilizing. But this was just the beginning. Because once those missions connect, they stop feeling temporary. Habitats remain active between crews. Power systems continue running without interruption. Communication networks stay online. Equipment gets reused instead of replaced. And slowly, what used to be a series of visits becomes a continuous presence. Then came the moment that changes everything. Operations no longer depend on Earth in the same way. Resources are processed locally. Fuel is produced on the surface. Infrastructure supports itself. And each new mission builds on what's already there instead of starting over. That's when the advantage stops being theoretical and becomes permanent. Because the side that reaches this point first doesn't just move ahead, it moves differently. Costs begin to drop. Speed begins to increase. Expansion becomes easier. While others are still planning complex missions from Earth, this system is already running, improving, and scaling in real time. And it wasn't just about efficiency, it was about control. Because once a base is fully operational, every new mission entering that environment has to adjust. Landing zones are already defined. Infrastructure is already placed. Movement is already structured around existing systems. Then came the most unsettling realization. The race doesn't end when someone arrives. It ends when someone stays. Because at that point, you're no longer competing with a plan, or a mission, or a promise. You're competing with something that already exists. Something that grows while you're still catching up. And if China reaches that stage first, then the United States won't be racing to the moon anymore. It will be trying to enter a system it didn't build. And by the time that happens, the outcome won't be decided by who can get there. It will be decided by who got there early enough to never have to leave.